Okay, so in the history, and I said a couple of algorithms and issues, but neural networks look like this. So this is a simple neural network, and this one is a simple recurrent neural network. So recently we use CNN or LSTM or some other network architectures, but these ones are conventional, old-fashioned neural network layers. But still, even now, we use these feed-forward neural networks somewhere in the deep networks. Let's take a look at these feed-forward neural networks first. And we have input X. And in this case, X is in a two-dimensional space. But if we have an image like this, like a 10 by 10 image, then it will be a 100-dimensional vector. In that case, X will be 100-dimensional vector. When it is an image, then we can use the CNN, and when we apply the CNN, then we can use a 10 by 10 image as it is. But in the feed forward neural networks, then we need the vector, so we can vectorize image into a 100-dimensional vector. Then we can feed this vector to the neural network. Okay, so again, for feed forward neural networks, the input should be a vector. Okay, then we have a two-dimensional vector, and we have a matrix. So in this figure, we don't have bias for simplicity, but we can have bias. So we don't have a B here. So it's 1, and it can be connected to all the nodes. But anyway, so we have a matrix here. Okay, 2 by 3, so which is this matrix. So we multiply this matrix and vector so that we have a three-dimensional vector. And we can add this bias, and then we can apply simple nonlinear function. So we have H. H is a hidden layer, and we can stack more layers on top of this. So this one, we have matrix here, which is WHY, and we multiply this matrix with this vector, and we can have bias here too, and then we can have the output of this neural network. So if you want, you can stack like this. We can continue. So this is feed-forward neural networks, and what about the recurrent neural network? So basically, recurrent neural networks are the same as feed-forward neural networks, except these recurrent connections here. So in this equation, I just put the subscript t here, but in the feed-forward neural network, there is no time in this equation, so this subscript can be omitted. Okay. So without the subscript, we can write down these equations. But to compare this equation with the recurrent neural network, then I just put the subscript. Okay. Again, the subscript means nothing in feed-forward neural network because we don't consider a temporal structure at all. But in the recurrent neural network, we consider the temporal sequence. So instead of x, we have x of t, and it goes up, and we can make a hidden layer. But at the same time, when we feed this x, then also the previous hidden representation comes back to make the next hidden state. So h sub t is a result of this function, and this function has this term and this term and this term. These two terms are exactly the same as these two terms in the feed-forward neural networks, and only this term is new term in the recurrent neural network. And in this term, we have t minus 1. So by this t minus 1, t means something. Again, by this term, now recurrent neural network can have a memory. By definition, this W sub HH is a square matrix because we have the same dimension. So by this, now recurrent neural networks can memorize something as much as we need. Okay, and then the output layer is the same as feed-forward neural networks. So this is basic equations of neural networks. So basically, matrix and vector multiplication, and then the addition of bias, and then applying some nonlinear function, and then stack these layers again and again and again to make it deep. And in the previous slide, I talked about the activation functions. Okay, so I just said a nonlinear function, sigma. For sigma, we can think of many different functions. Okay, so first of all, we can think of just a linear function. And usually we don't use a linear function because we need the nonlinear function to make a neural network to be a nonlinear function. Okay, so we need the nonlinear activation. So usually we don't use this one. And as long as we have nonlinear function, then neural network will be a nonlinear functions. From input to output, if this sigma is linear, then the whole neural network will be a linear functions from x to y. To make this neural network to be nonlinear functions, we need the nonlinear activations here or here. So this one is piecewise linear. That's good. And also hyperbolic tangent or sigmoid function. Usually hyperbolic tangent or sigmoid functions were popular long time ago. And this one is piecewise linear or hard hyperbolic tangent. So basically it looks the same, but we have hard decision. Or we can use a threshold, which is not popular, and sine function is not popular. In deep learning era, we can use hyperbolic tangent, sigmoid, and sometimes hard hyperbolic tangent. Okay, and then recently, rectified linear unit functions are more popular. So ReLU is this one. And implementation of ReLU is really simple. Y is max 0 and x. When the x is negative, then the y will be 0. And when x is positive, y will be x. Okay, so this one is a nonlinear function. But in this area, the derivative of function is 0. Okay, the value is 0 and the derivative is 0. And for this part, the value is x. The derivative of this function is 1. Okay, that is important, so we're going to talk about it later. And this one is a leaky ReLU. Leaky ReLU is a little modification of ReLU because in this ReLU, if the input is negative, then the output is 0. Then there is no difference between this one and this one at all. So the leaky ReLU says, why don't we have a little difference here? So instead of identity function, for the negative area, instead of identity function, why don't we have a slight value here? So in this figure, it looks like a big number, but usually something like a 0.02 or 0.01 or something. Or instead of fixing this slope, then why do we have a parametric variable a? So that is parametric ReLU. Okay. So recently in deep learning, these functions are more popular. Okay. And there are some other functions too, like noise activation functions and so on. Now let's talk about forward propagation. In neural network, there are two propagations. First one is forward and second one is backward. Okay, so let's assume that neural network is already trained. Okay, so we're going to talk about this training later. So if it is trained already, then prediction or classification can be done by forward propagation. And the propagation goes from input to output, and we call it inference or recognition. Okay, so given this input x, it goes to the next layer. It's a simple operations, multiplying the matrix to this vector and then add some bias if there is, and then apply the nonlinear function, and that's it. And we can go to the next layer and then next layer. And if it is the last layer, then we can generate the output. Okay, that is the forward propagation. So if it is a binary classification, then one node is enough, right? So depending on this y, if the value of y is less than 0.5, then it is class 1, otherwise it's class 2. Or if it is a regression, then let's say the y is the temperature, then given this input x, then we can estimate the temperature of this room. Okay, that's what forward propagation does. Okay, so the last layer can be slightly different. So in the middle of this input and output, then the activation functions are simple, the sigmoid or hyperbolic tangent or ReLU and so on. So we can choose one of these activation functions, but the last function is special. So if we want to make probability from the output, then we can use softmax or a sigmoid function. We already talked about this sigmoid function and softmax in the regression chapter. As I said already, for logistic regressions, we want to model the categorical variables, and in the linear regressions, we want to model the continuous variables. And if we have multi-classes, then instead of just the simple Bernoulli, we can use categorical distributions based on this softmax.